5, 6, 7, 8.
It's time for Maths with Mr. Thomas.
Chapter 8, lesson number 7. Stationary points using the second derivative. Now if we think back to higher, let's look at the first derivative first of all. So we learned that when we differentiate f of x, we get the first derivative f dash x, and really that gives us the rate of change of the function with respect to x. If we are thinking about it graphically, well really, if you differentiate, you can get the gradient of a curve at a certain point, or the gradient of the tangent to the curve at that point. And we already know that when we differentiate, and if f dash a is going to be bigger than 0, then it means f of x is going to be increasing at x equals a. In other words, the gradient will be positive. If we get f dash a is less than 0, then it means the function will be decreasing at that point x equals a. And if we get f dash a equals 0, what does that mean? Perfect! It means that the function, the graph, is going to be stationary at x equals a. Woo! So we already know that. But let's take that a bit further. So if f dash x equals 0, then we are going to get a stationary point, and really we're going to have a maximum or a minimum or a point of inflection. And what we've done so far is we've worked out what type of stationary point we have using a nature table. However, we can also use the second derivative. The second derivative, f double dash x, finds the rate of change of the gradient of f of x with respect to x. So really, it tells us how the slope is changing at each point on the graph. Let's look at these examples here. So if you're looking at these two straight lines, well, you know straight away that there is a constant gradient for both of these. There is no change in the gradient, it is just staying as it is. So the second derivative for them will be 0. Looking at these two lines here though, well, you can see that the gradient is increasing. And it's the gradient of, say, take the gradient here, well, let's put in a tangent at that point. Let's go a bit further along. If you put in a tangent there, well, that's going to be a bit steeper. If you go further along, put in your tangent, it's even steeper. Put in the tangent here, again, that's going to be even steeper. So you can see that the gradient is becoming steeper, so the gradient is increasing. It's the same with this one as well. If you put in the gradient here, so if you put in a tangent and then put in a tangent further along, well, the gradient for this one is going to be above the gradient for this one. Again, if you keep going further along, well, the gradient again is going to be a higher value. The gradient here, again, it's going to be a higher value. So really, the gradient as you move from left to right is going to be increasing. And what does that mean when the gradient is going to be increasing? Well, it means that the second derivative will be positive. And what we can say with that is it is going concave up. So when the gradient from left to right is increasing, then your curve will be concave up. If we look at these curves here, well, you can see for this one, again, let's take a random point and just draw in the tangent. So the gradient at that point, you could work out what that would be. You could work out the gradient here. If you go draw the gradient in there, well, it's going to be less than the previous one. Or if you draw in the gradient there, which is kind of already done, well, that's going to be less again. If you draw in the gradient here, again, that is going to be less. So from left to right, well, the gradient is decreasing. It's the same here if you work out the gradient at that point, or the gradient at that point, the gradient at that point. As you go from left to right, well, the gradient is going to be decreasing. If you've got the tangent drawn in there, or in here, or in here, or in here, you can see that the gradient of those tangents is decreasing as you go from left to right. What that means then is because the gradient is decreasing, the second derivative, what do you think it'll be? Too good. It will be negative. And one way of saying that is the curve is going concave down. So concave up is when the gradient is increasing. Concave down is when the gradient is decreasing. So the second derivative can be used to investigate the nature of stationary points. So remember, a stationary point, dy by dx equals 0. If the second derivative is bigger than 0, then it means the stationary point is going to be a minimum. Remember, when it's bigger than 0, it's going to be concave up. So your curve will be going something like that. The gradient will be increasing from left to right, giving you then a minimum. If the second derivative is less than 0, then it means that the gradient is going to be decreasing, and that will give you a maximum turning point. So if it's decreasing, the gradient decreases, it's going to be concave down. Again, if you had that drawn in, well, it would look something like that. You can see the gradient there is steeper, and then it's becoming a lot more shallow. And then after that, the gradient would be 0, and it continues to decrease. So you can see that you would end up with a maximum. If the second derivative equals 0, then really the stationary point could be a maximum or a minimum, or it could be a point of inflection. And really, to find out which, you would have to use a nature table. A way that I quite like to remember this is using these two faces. So if the second derivative is bigger than 0, then it means the gradient is going to be increasing. And if the gradient is increasing, then it means that it's going to be a smiley face. So if the change in the gradient is going to be positive, you've got these wee positive eyes here, and it's going to be looking something like that. It's positive, it's a smiley face. And that gives you the minimum. If the second derivative is less than 0, then that's going to be below 0. So that's going to be a sad face, it's going to be negative. If you have that, well, you can see here it's drawn in, the gradient from left to right is decreasing, which gives you a maximum. This is just something daft that may help you remember, or it may not. It's entirely up to you. Let's try some examples though. So example 1, find the nature of the stationary points of the curve y equals x squared. So that is what we're starting with, y equals x squared. We know for stationary points we have to differentiate. So dy by dx equals 2x. How do we know when stationary points occur? Perfect. Stationary points occur when dy by dx equals 0. Perfect. So set that first derivative, dy by dx equal to 0. Therefore x is going to be 0. Brilliant. Good. So we've worked that out. We now need to think about the nature of the stationary points, and for that I suppose you could use a nature table, but this lesson here is all about using that second derivative. So let's look at the second derivative. To get the second derivative, we differentiate dy by dx. So differentiate dy by dx, we get d2y by dx squared. And if you differentiate 2x, you get, brilliant, you get 2. Perfect. From there then, well, we're thinking, right, well, we've got the second derivative, that is going to be 2, but we want the second derivative at the point when x equals 0. So when x equals 0, well, that second derivative is still going to be 2. So the second derivative will remain as 2, which is going to be bigger than 0. If it's bigger than 0, then it means you're going to have the gradient increasing. And if it increases, you're going to be concave up the graph. The gradient is going to be increasing. And because of that, remember, if it's positive, you've got the wee positive eyes, it's a smiley face, so you're going to have a smiley face there, and you're going to end up with a minimum turning point. Example 2, determine the coordinates and nature of the stationary points on the curve y equals 2x cubed, take away 3x squared, take away 12x. Once again, for the stationary points, you need to differentiate. So dy by dx equals, James, what would you have? Brilliant, you would get the 6x squared, take away 6x, take away 12. Good. So we've got the first derivative, and we know stationary points occur when dy by dx equals 0. So set that first derivative equal to 0. So the 6x squared, take away 6x, take away 12 equals 0. To solve for x, what would you have to do, Megan? Good, you would have to factorise. So factorising that is what you would get. Can you take it any further? Good. You can factorise the x squared take away x take away 2 to become x take away 2, x plus 1. And you've obviously got that 6 there. That gives you two different values, and the values would be, good, values are 2 and negative 1. Perfect. So you're thinking, right, well, what happens when x is 2? What happens when x is 1? Let's get the y coordinates as well. So the y coordinates, we know when x equals 2. In order to work out y, well, we're just replacing the x with 2 into the original equation. So it'll become 2 times 2 cubed, take away 3 times 2 squared, take away 12 times 2. If you work that out, well, you get negative 20. So we know there's going to be a stationary point at 2, negative 20. When x equals negative 1, do the same thing, replace x in y equals with negative 1. Therefore, y would equal, and work that out, you would have 2 times negative 1 cubed, take away 3 times negative 1 squared, take away 12 times negative 1. Work that out, and you get 7. So you know there is a stationary point at negative 1, 7. So we know our stationary points, but again, you've got to think about the nature. To get the nature, you could use a nature table, or you may be asked to use the second derivative, or you may want to use the second derivative. So we've got the stationary points at negative 1, 7 and 2, negative 20. We started off with y equals, and we have that first derivative. For the second derivative, let's differentiate again. So differentiating that d2y by dx squared, that would equal, we'll differentiate the first derivative, that gives us 12x, take away 6. So we've got the second derivative now. So what we want to do is we want to think, right, well, when x equals, we've got a stationary point at negative 1, 7. So when x is negative 1, what is the value of this second derivative? Well, d2y by dx squared would equal, well, you've got 12 times negative 1, take away 6. Work that out and you get negative 18. Because you've got a negative for that second derivative, it means it is going to be concave down. And when it's your negative, just think about this sad face here. It's a negative, it's a sad face, which means you are going to have a maximum. And you've got a maximum because the second derivative is less than 0. So second derivative is less than 0, it implies there is a maximum turning point. Let's take the other value. So there was a stationary point at 2, negative 20. Well, when x was equal to 2, let's find out the nature using the second derivative. So d2y by dx squared would equal, let's replace x with 2. So we've got 12 times 2, take away 6. Work that out and we get positive 18. Because it's a positive, it's going to be concave up. Woo! And because your second derivative is bigger than 0, because it is positive, just think about the wee happy face. It's a wee happy face, it's all smiley, so that point there will be a minimum. So there is a maximum turning point at negative 1, 7 and a minimum turning point at 2, negative 20. Example 3, find the coordinates of the stationary points on the graph of f of x equals 4x cubed, take away x to the power of 4, and determine their nature. So we're starting off with f of x equals 4x cubed, take away x to the power of 4. We know that we're going to be differentiating. So differentiate to find the stationary point, so f dash x would equal, well done, 12x squared, take away 4x cubed. And to get the stationary points, we know they occur when? Brilliant, they occur when dy by dx, or in this case f dash x, equals 0. So set that first derivative equal to 0. Factorise, if you factorise that, you can take out the 4x squared as a common factor, and that would give you the two values, Sam, of, good, it would give you x equals 0 and x equals 3. So we know there is going to be a stationary point at x equals 0 and x equals 3. Let's find out the y value as well. So let's take the 0 and the 3. So f of, let's replace x with 0. So f of 0 gives us, well, we've got 4 times 0 cubed, take away 0 to the power of 4. If you work that out, well, that just works out to be 0. So there's going to be a stationary point at 0, 0. When x equals 3, do the same thing, replace x with 3, so we'd have 4 times 3 cubed. Take away 3 to the power of 4. If you work that out, you get 27. Meaning then, there is a stationary point at 3, x is 3, and y is 27. So there's a stationary point at 3, 27. What we need to do next is think about the nature. How do we think about the nature? Well, again, you could just use a nature table or use the second derivative. I'm using the second derivative because that's what this lesson is all about. So, the second derivative, well, we're going to have to differentiate f dash x. Differentiating f dash x will give us f double dash x, and that is 24x, take away 12x squared. And let's take then the stationary point first of all with 0, 0. So when x equals 0, sub that into the second derivative. So f double dash 0 will equal, we'd have 24 times 0, take away 12 times 0 squared. You're perfectly right, that just works out to be 0. Well done. What happens when the second derivative works out to be 0? Does anybody remember? Good. You have to use a nature table. So if the second derivative works out to be 0, it means it could be a maximum, could be a minimum, or a point of inflection. So you have to use the nature table for that. So your nature table, you've got x, 0 was the value of x that we found for the stationary point. Pick a value just before and just after. Sub that into the first derivative, f dash x, the 12x squared, take away 4x cubed, and then work out if it's going to be a positive or a negative to determine the slope. So if we put in a value less than 0 into f dash x, say negative 1, well, you end up getting a positive value. So the graph will be increasing at that point. When you sub in 0, well, you should just be getting 0 because you're saying it's a stationary point. Just double check. If you put 0 in here, yes, you do. You get 0, meaning that would be perfectly flat. So it's a stationary point. And if you put in a value bigger than 0, let's say 1, so 12 times 1 squared, take away 4 times 1 cubed, well, again, you get a positive. So the graph, again, will be increasing after that stationary point. Meaning then that this will be a point of inflection. So you can say that 0, 0 is a point of inflection, and you're proving that with the nature table. Let's look at the other point, though. There was also a stationary point at 327. Don't forget about me. And you can say that when x equals 3, well, put that into the second derivative. So f double dash 3 works out to be 24 times 3, take away 12 times 3 squared. If you work that out, anybody know what you would get? Good, you do get a negative, and it's negative 36. Because that second derivative works out to be a negative, well, it's going to be concave down. If it's concave down, well, it's looking something like that. The gradient will be decreasing. If the gradient is decreasing, it's going to be a negative, so you would end up with this sad face here. If you end up with the sad face, then it means this point here, you can see that that will be a maximum. So since the second derivative is less than 0, you know 327 is a maximum turning point. That is it for stationary points using the second derivative. Try these questions in the book, page 51. Check your answers as you go. Feel free to use this wee guy if it helps you out. Best of luck. Bye.